You know, so many things we use every day, from the engine block in your car to the frying pan in your kitchen, they all start their life as this fiery, glowing liquid. Today, we're going to dive into the ancient art of metal casting. It's this incredible process of turning molten metal into the solid shapes that, well, literally build our world.
Let's just start with the biggest question right off the bat. How in the world do you take something as wild and unruly as molten metal and convince it to hold a specific permanent shape? I mean, it seems like it should be impossible, right? But it's actually just a brilliant piece of engineering.
And the answer is a process called casting. At its heart, the idea is, well, it's just beautifully simple. You make a container, a mold, with a hollow space inside that's the exact shape you want. You pour in the liquid metal, you let it cool down and get solid, and voila, you've captured the form. Really, when you boil this whole massive industrial process down, it just comes down to two things. That's it. You need this super hot liquid metal, and you need a carefully crafted mold that's going to give it a home and a shape.
Okay, so the principle is simple, but as you can imagine, the execution is anything but. There's not just one way to cast metal. Oh no. Depending on what you're making, how complex it is, and how many you need, engineers have to pick the right path. So let's look at the three main ways they do it.
And choosing the right method is absolutely everything. For a really complex, maybe one-off part like a giant engine block, sand casting is perfect because it's so incredibly versatile. But if you need to crank out thousands of identical, super precise parts, you're going to turn to die casting. That uses a durable, reusable metal mold that's actually called a die. And for making things that are just incredibly long, think steel beams or pipes, continuous casting does, well, exactly what it sounds like.
So you might be wondering, how do you make that perfect hollow space in a sand mold? You use something called a pattern. Think of it like a physical blueprint. It's a full-size model of the thing you want to make. You press this pattern into the sand to create that perfect impression, that cavity that the molten metal is eventually going to fill.
You know, to really get a feel for how this all works, let's imagine we can follow a single drop of molten metal on its incredible journey. From the second it leaves the furnace to the moment it becomes solid, it follows a very, very specific path.
And this right here is its roadmap. The journey starts with a pour from a vessel called a ladle. It enters the mold through the sprue, travels down a whole highway system of runners and gates, and finally reaches its destination in the cavity. And the whole time it's being helped by a support system of risers and vents. Let's break all of that down.
All right, step one. The journey begins right here, in the ladle. This is basically a giant, super tough bucket designed to safely carry and pour metal that can be thousands of degrees hot. This is where our little drop of metal starts its big trip.
The very first part of the mold it meets is the sprue. This is the main entryway. It's a vertical channel that guides all that hot metal from the top of the mold down into the rest of the system. You can absolutely think of it as the front door. Now, once it's inside, the metal can't just splash around everywhere. It has to be directed very carefully, and that's the job of the runner. These are like the hallways or the highways that branch off from the bottom of the sprue, and they distribute the liquid metal efficiently to exactly where it needs to go.
And at the very end of that highway is the final doorway, the gate. This is the precise entry point where the metal leaves that runner system and finally flows into the space that's going to become the finished part. And trust me, the size and placement of that gate is absolutely critical.
And here we are, the final destination, the cavity. This is the whole reason the entire system exists. This meticulously shaped void is where the liquid metal finally comes to rest, cools down, and hardens, taking on the shape of the final part. This is the moment of creation, right here. This shows us something really cool. The cavity forms the outside shape, sure, but what if you need a hole or some kind of complex internal tunnel? How do you do that? Well, that's where a core comes in. It's a precisely shaped piece that you place inside the cavity before you pour. The metal flows all around it, and when you're done, you've got your perfectly formed internal features. So metal has this funny little quirk. As it cools and gets solid, it shrinks, and if you're not careful, that shrinkage can leave a big sunken defect in your part. To prevent that, engineers add a riser. It's basically an extra tank, a reservoir of molten metal, that acts as a backup, feeding more liquid into the main cavity to make up for that shrinkage. Pretty clever, right?
Think about it. When you pour all that liquid metal in, what happens to the air that was already in the cavity? It needs to go somewhere. That's the job of the vent. These are tiny little channels that let the mold breathe, allowing all those trapped gases and air to escape, so they don't form bubbles in your final part.
So,
We've designed this perfect, elaborate journey for our molten metal. But what happens when things go wrong? Because they do. A failure at any one of these steps can lead to a whole range of pretty serious defects.
And here's some of the usual suspects, the things that engineers are always working to avoid. You've got things like porosity, shrinkage, cold shuts, misruns, flash. Each one of these tells a little story about a problem with temperature or flow, or maybe the mold design itself. And this is exactly why those vents are so important. If the gases can't get out, they get trapped as the metal solidifies, creating these tiny, unwanted bubbles or voids. We call this porosity, and it can seriously weaken the final part, turning what should be a strong component into a major point of failure.
In casting, timing and temperature are absolutely everything. If the metal cools down just a little too quickly, you can get what's called a misrun, where it literally freezes before it's finished filling the cavity. A related problem is a cold shut. That's where two streams of metal meet up, but they're just too cool to fuse together properly, creating a hidden crack deep inside the part.
And finally, there's flash. You've probably seen this before. It's that thin, extra lip of material you sometimes find on cast parts. It happens when the two halves of the mold don't seal up perfectly, and a little bit of that molten metal squeezes out through the gap. And then, of course, that has to be ground off in a whole extra costly step. So you see, a successful cast isn't just about melting and pouring. It's this incredibly delicate dance. It really is a story of perfectly controlled flow, super precise temperature, and just flawless timing. And it's all happening inside a hidden, enclosed space where you can't even see it.
Which brings us to one last really important question. After seeing how complex this is and all the ways it can go wrong, why is casting still a cornerstone of modern industry? Well, the answer is pretty simple. There is no other process that can create such complex and strong shapes from a single piece of metal this efficiently and at such a massive scale. It lets us design parts for their strength and function, not just for how they can be bolted together. And that right there is why this ancient art remains at the absolute heart of modern engineering.